Hello and welcome to Physics Before Bed. If you enjoy diving deep into the wonders of the universe in a calm, educational way, be sure to like this video and subscribe to join our community of curious minds. And hey, if you're listening or watching right now, let me know where you're tuning in from. Is it from a quiet corner of your room, or perhaps somewhere cozy in the vast expanse of space? Metaphorically speaking, of course. Time is a funny thing, isn't it? It can seem so fluid, yet it defines everything we experience. In today's journey, we're going to dive into one of the most mind-bending concepts in physics, time. We often think of time as this constant, ticking thing, but what if I told you it's far more mysterious than that? From the ancient measurements of the sun and moon to the mind-altering theories of space-time and quantum physics, time is much more than just a ticking clock. So, settle in, relax, and let's explore what time really is as we unpack this beautiful, complex phenomenon and its fundamental role in shaping everything we know about the universe. What is time? It's a question that has both fascinated and baffled humanity for centuries. On one hand, time seems to be something very tangible. After all, we measure it every day in seconds, minutes, and hours. We plan our lives around it, and we know when the sun will rise and set. But on the other hand, time is elusive, slippery, and deeply mysterious. It's a concept we can't quite touch, feel, or fully understand, yet it shapes everything in our lives, from the beating of our hearts to the movement of the stars. Time is, in a way, both abstract and very real at the same time. The ancient Greeks were among the first to ask profound questions about time. One of the earliest philosophers to tackle the concept was Zeno of Elea. He's famous for his paradoxes, ideas that challenge our common sense understanding of time and motion. For example, Zeno presented the paradox of Achilles and the tortoise. In this paradox, Achilles, a swift runner, is chasing a tortoise in a race, but Zeno argues that Achilles can never catch up to the tortoise, no matter how fast he runs. This is because every time Achilles reaches the spot where the tortoise has moved a little further ahead. Zeno's paradoxes made people question the nature of time and movement. Are they continuous, or are they made up of discrete steps that we don't fully grasp? In addition to Zeno, Augustine of Hippo, a Christian philosopher who lived in the 4th and 5th centuries, pondered time in a different way. In his work Confessions, Augustine famously said, "What is time? If no one asks me, I know. If I wish to explain it to him who asks, I do not know." Augustine's contemplation touches on an important point. Time is something we experience, but when we try to define it, it becomes slippery. We can measure it, we can feel it, but when we try to grasp it intellectually, it slips away, like trying to hold water in our hands. Fast forward 1,000 years, and the conversation about time begins to take on a more scientific shape. In the 17th century, Isaac Newton, one of the most influential scientists in history, proposed that time is absolute. According to Newton, time flows uniformly throughout the universe, independent of the events or objects happening within it. For Newton, time is like a cosmic clock, ticking steadily and consistently, no matter where you are or what's happening around you. This is a comforting, predictable view of time, a view that made sense for centuries and helped explain how objects in motion interact with one another. But, as with so many things in physics, this tidy picture started to break down when scientists began to explore the universe on a much larger scale. Albert Einstein, in the early 20th century, completely revolutionized our understanding of time with his theory of relativity. Einstein's work introduced the idea that time isn't absolute at all, it's relative. Time can stretch and contract depending on how fast you're moving and how close you are to a massive object like a planet or a star. For example, if you were to travel at nearly the speed of light, time for you would slow down compared to someone who was standing still. This phenomenon is known as time dilation. But Einstein didn't just make time relative, he also showed that time is intimately connected to space. The two are woven together into what we call space-time, a four-dimensional fabric that makes up the very structure of the universe. This was a huge departure from Newton's view of absolute time. Einstein's space-time is much more like a piece of rubber that can be stretched and distorted by massive objects. If you imagine a heavy ball placed on a rubber sheet, it will create a dip in the sheet, and objects nearby will roll toward the ball. Similarly, massive objects like stars and planets curve space-time, and this curvature is what we experience as gravity. But there's more to time than just these physical ideas. Time also has a subjective quality, something that we feel in our daily lives. We experience time differently depending on the situation. For example, when we're having fun, time seems to fly by. But when we're bored or waiting for something, time seems to drag on. This subjective sense of time, often referred to as psychological time, can seem to flow faster or slower depending on our mental state. And this is where the divide between the scientific and philosophical views of time becomes especially interesting. For centuries, philosophers have debated whether time is something external, existing independently of us, or if it's merely a product of our minds. Immanuel Kant, an 18th century philosopher, argued that time doesn't exist out there in the world, but rather is a framework that our minds impose on the events we experience. According to Kant, time is an essential part of how we perceive reality, but it's not something that exists independently of our consciousness. In modern physics, however, time is very much an external physical phenomenon. It is a measurable, quantifiable aspect of the universe, central to the theories that describe how the universe works. Whether it's the ticking of a clock or the movement of galaxies, time is woven into the very fabric of reality. And yet, just like Augustine said so many centuries ago, even today we still don't fully understand what time is. We've made incredible progress, but the deeper, more mysterious aspects of time remain elusive. As we look back on the historical evolution of time measurement, we can see how humans have moved from philosophical musings to developing ways to measure and quantify time with increasing accuracy. From the sundials of ancient Egypt to the atomic clocks of today, we've continually sought to define and control time. In many ways, our understanding of time has shaped the way we interact with the world, whether it's scheduling our lives down to the second or using the very measurement of time to navigate the cosmos. And yet, even as we refine our tools and deepen our understanding of time, we find that the essence of time, its nature, its flow, and its origin, remains a tantalizing mystery. Whether it's in the tick of a clock or in the vast sweep of the universe, time is something we can measure but still don't entirely grasp. As we continue on this journey to explore time, we'll discover not only the mathematical and scientific principles that govern its behavior, but also the profound philosophical implications that time has had on human thought for centuries. Time is far more than something that passes. It is a concept that shapes everything we understand about existence. In the early days of human civilization, time was something that people needed to measure, but they had no clocks or watches to rely on. Instead, ancient societies used the natural world as their guide, observing the sun, moon, and stars to mark the passing of time. One of the most common methods of measuring time was the sundial, a simple yet effective tool that dates back as far as the Egyptians. Sundials worked by casting a shadow as the sun moved across the sky, providing a visual way to track the time of day. As the shadow shifted, it marked the progression of time from morning to evening, allowing people to structure their days. In ancient Egypt, timekeeping was essential for organizing society, particularly for agriculture. The division of the day into specific hours was crucial, especially when it came to working the land. The Egyptians had a system of 12 hours for the day and 12 hours for the night, based on the observation of the stars and the position of the sun. This 12-hour division was not based on the length of the hour that we use today, but rather it was tied to the seasonal changes in the length of daylight. As the seasons changed, the length of the daylight hours varied, so the hours themselves would stretch or shrink accordingly. This system was simple, but it set the stage for more precise ways to divide and measure time. The Babylonians also played a key role in early timekeeping. They were one of the first to divide the day into equal hours. Their system was based on the number 12, a number that held great significance in their culture. This division led to the creation of the 60-minute hour and the 60-second minute, which are still in use today. It was the Babylonians' keen interest in astronomy and their mathematical advances that helped to formalize the division of time in this way. They saw the celestial bodies as symbols of order and structure, and the regular movement of the stars and planets offered a natural pattern to follow. As time moved forward, so did the methods for keeping track of it. The mechanical clock, one of the most important inventions in the history of timekeeping, began to take shape in the early Middle Ages. These early clocks were powered by weights and gears, with the first recorded mechanical clock built in the 13th century. These clocks were primarily used in monasteries and churches to help regulate prayer times, but over the next few centuries, they began to make their way into more public spaces. The invention of the mechanical clock marked a huge leap in precision, allowing for a more standardized and reliable way to track time, independent of the natural world. No longer would people have to rely on the changing position of the sun or the moon. Time could now be measured more accurately, and it was available at the turn of a wheel. But the mechanical clock was not the final step in humanity's quest to measure time accurately. There were still challenges to overcome, particularly when it came to measuring time across vast distances. For sailors, one of the most pressing concerns was how to calculate longitude while at sea. Without a reliable way to track time, navigators could not determine their precise location. This challenge was finally addressed in the 18th century by John Harrison, an English clockmaker who developed the marine chronometer. Harrison's invention was revolutionary because it was able to keep time accurately enough to allow sailors to determine their longitude at sea. Before the marine chronometer, the best navigators could do was estimate their position, often leading to errors that resulted in dangerous and costly mistakes. Harrison's chronometer was so precise that it allowed for the accurate measurement of time, even during long ocean voyages. This invention had a profound impact on global exploration, trade and navigation, changing the course of history and enabling sailors to travel the world with greater confidence and accuracy. At the same time, back on land, scientific advancements were pushing the boundaries of our understanding of time. Isaac Barrow, an English mathematician and theologian, made important contributions to the study of rates of change, which would later be formalized into the field of calculus by his student, Isaac Newton. Barrow's work laid the groundwork for understanding how things change over time, which is a fundamental concept in both physics and mathematics. Barrow's contributions to the development of calculus helped to formalize our understanding of time as a measurable quantity that could be treated mathematically. This was a key shift in the way we think about time, as it moved from being just an observable natural phenomenon to something that could be analyzed and manipulated mathematically. With the development of mechanical clocks, the invention of the marine chronometer, and the mathematical advancements brought about by Barrow and others, humanity had made tremendous strides in its ability to measure and understand time. But the story doesn't end here. As accurate as these timekeeping methods were, they were still based on the assumptions and principles of classical physics. The world of classical mechanics, with its absolute time and predictable laws, would soon be challenged by a groundbreaking new theory that would revolutionize our understanding of time altogether. As we move forward in history, the shift from classical to modern physics would bring with it an entirely new way of thinking about time. In the world of classical mechanics, time was seen as a constant, flowing at the same rate for everyone, everywhere. But in the early 20th century, Albert Einstein would introduce a new understanding of time, one that was far more complex and surprising. In his theory of relativity, time would no longer be absolute. It would be relative, bending and stretching depending on speed, gravity, and motion. This new view of time would forever alter the way we think about the universe and our place in it. The history of time measurement is a fascinating journey. From the ancient civilizations that first began dividing the day into hours, to the mechanical clocks that helped regulate society, to the groundbreaking innovations that allowed us to measure time across vast distances. Each step along the way has brought us closer to a deeper understanding of time, but as we'll see, the true nature of time remains one of the most profound mysteries of all. When Isaac Newton introduced his laws of motion in the late 17th century, he also presented a revolutionary view of time, one that would dominate scientific thought for centuries. Newton's idea of time was absolute. He believed that time exists independently of the objects and events that occur within it. In his famous work, Philosophia Naturalis Principia Mathematica, which is often referred to simply as the Principia, Newton described time as a constant, unchanging backdrop against which the entire universe unfolds. For Newton, time flows uniformly, everywhere and for everyone, regardless of the state of motion of any objects. It is a kind of cosmic clock that ticks away at the same rate throughout the universe, whether we are aware of it or not. This idea of absolute time was radically different from the perspective held by Gottfried Wilhelm Leibniz, a German philosopher and mathematician who was Newton's contemporary. Leibniz argued that time was not something that existed independently of the universe. Instead, he believed that time is relational. It only makes sense when there are events or objects that can be compared to each other. For Leibniz, time was the result of the relationships between objects, not a separate entity. Imagine a race between two runners. The time it takes for one runner to reach the finish line only exists because we can measure it against the motion of the other runner. Without the runners, time for Leibniz would have no meaning. The debate between Newton and Leibniz was one of the most intense intellectual conflicts of the 17th century. The two men had fundamental disagreements not only about the nature of time, but also about the nature of space and motion. Newton's absolute view of time was linked to his belief in a deterministic universe, where every event could be predicted if one knew the positions and velocities of all objects at any given moment. Leibniz, on the other hand, believed that the universe was dynamic and relational, and that the laws of nature depended on the relationships between objects rather than some preordained cosmic order. This debate would shape the development of physics for years to come, with Newton's ideas ultimately prevailing in the scientific community. The dominance of Newtonian mechanics, built on his conception of absolute time, led to the development of classical physics. Newton's laws of motion, which describe how objects move in relation to forces, assumed that time was a steady, unchanging ruler by which everything else could be measured. These laws provided a powerful framework for understanding the physical world. Whether you were studying the motion of a falling apple or the orbits of planets around the sun, Newton's laws worked under the assumption that time was the same everywhere and for everyone. This idea of absolute time became the bedrock of classical mechanics, and it served as the foundation for much of physics for the next 300 years. However, as time went on, some scientists began to question the certainty of Newtonian time. One of the most notable figures to do so was Henri Poincaré, a French mathematician and physicist who worked in the late 19th and early 20th centuries. Poincaré's work on the nature of chaos and determinism foreshadowed what we now call chaos theory. He pointed out that, even though Newtonian mechanics assumes a predictable, orderly universe, there are certain systems, such as the motion of the planets, that can behave in ways that are difficult, if not impossible, to predict. Poincaré suggested that small changes in the initial conditions of a system could lead to dramatically different outcomes. This idea would later become a cornerstone of chaos theory, which deals with the unpredictability of complex systems. While Poincaré did not completely reject Newtonian mechanics, he highlighted its limitations, especially when it came to the behavior of time in complex systems. Another key figure in the development of the idea of time was Pierre-Simon Laplace, a French mathematician and astronomer. Laplace is perhaps best known for his deterministic view of the universe. He famously proposed what is now known as Laplace's demon, an imaginary intellect that could, if it knew the position and velocity of every particle in the universe at a single point in time, predict every future event. For Laplace, time was something entirely predictable, with no room for uncertainty or randomness. Everything in the universe, according to Laplace, followed a strict cause and effect chain, driven by the laws of Newtonian mechanics. This view was in line with the concept of absolute time, where time was seen as an unchanging framework for the entire universe. Laplace's deterministic worldview was hugely influential, especially in the field of celestial mechanics, where the movement of the planets and stars seemed to follow predictable paths based on the laws of gravity. Yet, even Laplace's deterministic universe had its limits. While it provided an elegant and orderly picture of the cosmos, it did not account for the complexities and uncertainties that would later be revealed by quantum mechanics and the theory of relativity. As the 18th and 19th centuries progressed, the certainty of Newtonian time and Laplace's deterministic universe began to come under increasing scrutiny. The development of new scientific ideas, particularly in the realm of electromagnetism and thermodynamics, began to challenge the assumptions of classical mechanics. In the mid-19th century, James Clerk Maxwell, a Scottish physicist, formulated his equations that described electromagnetism, showing that the speed of light was constant and independent of the motion of the observer. This raised questions about the nature of time and whether it could be absolute in the same way Newton had proposed. By the late 19th century, scientists were starting to realize that time, as they understood it, was far more complicated than the steady ticking clock of Newtonian mechanics. This growing unease set the stage for a revolution in physics, one that would change the way we thought about time forever. The theory of special relativity, formulated by Albert Einstein in the early 20th century, would eventually replace the idea of absolute time with a new understanding, one where time is relative, depending on the observer's motion and position in space. This shift from Newtonian time to relativistic time was profound, and it would forever alter our understanding of the universe. No longer could time be treated as a simple, constant background to the laws of physics. Instead, time would be shown to be flexible, dynamic, and tied intimately to the fabric of space itself. But before Einstein's groundbreaking ideas could be fully realized, the classical mechanics framework, with its conception of time as absolute and predictable, would serve as the foundation for much of physics. The leap to relativity required building upon the ideas that came before, and it was in this intellectual space that the concept of time would truly be redefined. The philosophical debates between Newton and Leibniz, the deterministic ideas of Laplace, and the insights of Poincaré all paved the way for the next great breakthrough in physics. The stage was set, and the stage was set for Einstein to take us into a new era of understanding time, one that would challenge everything we thought we knew. In the early 20th century, Albert Einstein's theories of relativity changed our understanding of time in profound ways. But before Einstein's groundbreaking ideas could reshape physics, Hermann Minkowski, a German mathematician, introduced a concept that was key to unlocking the full potential of relativity. Minkowski recognized that Einstein's theory of special relativity, which dealt with objects moving at high speeds, could be better understood if we didn't think of space and time as separate, isolated entities. Instead, he proposed that they were deeply intertwined, united in a four-dimensional continuum. This idea of space-time was revolutionary. In Minkowski's vision, space and time were no longer simply coordinates in which objects exist, but part of a single, unified fabric that could be warped and stretched. Instead of thinking about time as just a ticking clock that runs independently of space, Minkowski showed that time could bend and stretch, just like the three dimensions of space. This meant that the experience of time could change depending on the observer's movement and position in space. If we could imagine the universe as a massive fabric, then events would leave marks on that fabric, stretching or shrinking the fabric itself depending on how fast an object was moving or how close it was to a massive object. Minkowski's four-dimensional concept of spacetime set the stage for Einstein's own work. Special relativity, which Einstein introduced in 1905, showed that time is not the same for all observers. The faster you move through space, the more time slows down for you. This is known as time dilation, and it's something that happens whenever you approach the speed of light. If you were travelling at nearly the speed of light, a clock on your spaceship would tick much slower compared to a clock on Earth. This means that if you travelled at such speeds and returned to Earth, you might find that less time had passed for you than for those who stayed behind. Einstein's equations, such as E equals mc squared, show that energy and mass are related, and these relationships are governed by the curvature of spacetime itself. But special relativity only explained what happens to time when objects are moving at high speeds through space. To fully account for time in more extreme scenarios, like when objects are near massive bodies such as stars or black holes, Einstein introduced general relativity in 1915. General relativity extended the ideas of special relativity by including gravity. According to general relativity, gravity is not a force that acts across space in the way Newton once described. Instead, it's the result of mass and energy bending spacetime. Massive objects like planets, stars, and black holes warp the fabric of spacetime around them, causing objects to move in curved paths. Time is also affected by this warping. The stronger the gravitational field, the more time slows down. One of the most famous and dramatic predictions of general relativity is that time runs more slowly near massive objects. For example, if you were near a black hole, time would pass much slower for you compared to someone far away from it. This phenomenon is known as gravitational time dilation. It's not just a theoretical idea, it's been confirmed by experiments. For instance, scientists have placed atomic clocks on airplanes and flown them around the world. When the clocks were compared to those left on the ground, they showed tiny but measurable differences, confirming that time had indeed passed more slowly for the clocks in motion. To understand the effects of space-time around a black hole more concretely, we turn to the work of Karl Schwarzschild, a German physicist who solved Einstein's equations for a point mass, like a star or planet, in the vacuum of space. Schwarzschild's solution revealed the existence of what we now call the event horizon. This is the point beyond which not even light can escape the gravitational pull of a black hole. The closer you get to this boundary, the more extreme the effects of time dilation become. For an observer near the event horizon, time appears to come to a stop. From their perspective, everything outside the black hole would seem to be moving faster and faster. Yet, for someone observing from a safe distance, they would see the person near the event horizon moving slower and slower as they approach the black hole. This gives us a truly mind-boggling view of time, one that becomes completely malleable depending on where you are in the universe. While Einstein's contributions were groundbreaking, he did not work alone. A key collaborator in understanding these new concepts of time was Leopold Infeld, a physicist who worked closely with Einstein. Infeld helped to refine the mathematical descriptions of time dilation, particularly in the context of more complex systems, such as rotating black holes or objects moving through curved spacetime. Infeld's work showed that time dilation wasn't just a curiosity for high-speed or high-gravity objects, but a fundamental part of how the universe works. In fact, time dilation is so deeply woven into the fabric of the universe that it has practical applications today. Satellites that orbit Earth need to account for both special and general relativistic effects to keep their timekeeping accurate. Without correcting for time dilation, GPS systems would quickly become inaccurate. As we look at these theories, one thing becomes clear. Time, as we once understood it, is no longer a simple, linear progression. It is not the absolute fixed quantity that Newton envisioned. Instead, time is deeply connected to the motion of objects, the curvature of space-time, and the distribution of mass and energy in the universe. It's no longer just a backdrop to the universe's events, but an active participant in shaping how those events unfold. Yet, even as Einstein's theories of relativity revolutionized our understanding of time, they did not answer every question. In fact, they raised a new one. How does relativity connect to quantum mechanics? In the world of the very small, where particles like electrons and photons exist, time seems to behave differently. In the quantum realm, particles can be in multiple places at once, and events can seem to happen without clear cause and effect relationships. This raises a fundamental question. Is time in the quantum world just as malleable and flexible as it is in relativity? And if so, how do we reconcile these two worlds? Relativity, with its smooth spacetime, and quantum mechanics, with its probabilistic, uncertain nature, these questions remain at the heart of modern physics. As we move forward, scientists are still searching for a unified theory that can combine the principles of quantum mechanics and general relativity, an understanding of time that works in both the vastness of the cosmos and the tiniest particles of the quantum world. Until that happens, time will remain one of the most intriguing and elusive concepts in physics, something that continues to shape our understanding of the universe in unexpected ways. In the next chapter, we'll explore how scientists are grappling with these questions and what the future might hold for our understanding of time, space, and the universe itself. Before Einstein, space and time were thought of as separate, distinct entities. Space was the vast, three-dimensional expanse in which all things existed, and time was simply the unchanging progression of moments from the past to the future. These concepts, though useful, never fully captured the true nature of the universe. But as Einstein's theories unfolded, this separation would no longer hold. Time, just like space, was part of a much larger, more intricate structure, a fabric that could bend, stretch, and warp depending on the presence of mass and energy. This new framework, called spacetime, fundamentally changed our understanding of the universe. Spacetime isn't just a backdrop where things happen, it's woven into the very fabric of the cosmos. Imagine space and time as two interwoven dimensions that can't be completely separated from one another. Just as you can't isolate length from width in a two-dimensional plane, you can't treat space and time as independent. They are inseparable, existing together in a unified four-dimensional continuum, where three of those dimensions represent space and the fourth represents time. In this view, every event that occurs in the universe has both a spatial position and a time at which it occurs. This revolutionary idea was solidified by Hermann Minkowski, a German mathematician and physicist, whose work on the relationship between space and time helped bring Einstein's theory of relativity to its full realization. Minkowski didn't just build on Einstein's theories, he fundamentally showed that time must be treated as a physical dimension, not something separate, like a ticking clock detached from the world. Minkowski's concept of space-time helped explain how the universe works, not just in terms of space, but in terms of how time and space interact. The more massive an object, the more it warps space-time. This warping, in turn, affects everything in its vicinity, including light. A simple way to visualize this is to imagine space-time as a stretched rubber sheet. If you place a heavy object on the sheet, it will create a depression, and smaller objects placed nearby will roll toward the heavy object. This is analogous to how massive objects like stars and planets create a dimple in the fabric of space-time, which affects the motion of objects around them. This insight was a crucial part of understanding gravity in Einstein's general theory of relativity. Gravity is no longer viewed as a mysterious force between masses. It's simply the result of objects moving through curved space-time. One of the scientists who extended our understanding of space-time in an important way was John Archibald Wheeler, an American theoretical physicist. Wheeler took the idea of space-time even further by introducing the concept of the geon. A geon is a hypothetical, localized object in space-time that carries gravitational energy. What makes a geon so interesting is that it represents a region of space-time that's held together by the very gravitational forces it generates, without requiring any matter to exist at its center. Wheeler's concept of geons helped shift how scientists thought about the relationship between matter, energy, and space-time itself. Instead of thinking of mass as the thing that warps space-time, Wheeler showed that space-time itself could contain the potential for gravitational fields, even in the absence of conventional matter. Another key contributor to understanding the behavior of space-time, particularly near black holes, was Roger Penrose, a British mathematical physicist. Penrose's work in the mid-20th century provided a clear way to visualize how space-time behaves under extreme conditions, such as near black holes. He introduced Penrose diagrams, a tool used to map out the warping of space-time in a two-dimensional graph, showing how light and matter travel within the curved space around black holes. These diagrams are particularly useful because they help us understand how time and space are distorted by the intense gravity of black holes. As objects get closer to a black hole, time seems to slow down relative to someone far away from it. The Penrose diagram visualizes this, showing that as an object approaches the event horizon of a black hole, time stretches infinitely, from the perspective of an observer watching from a distance. Penrose's diagrams also allowed for an elegant understanding of the singularity, the point at the center of a black hole where spacetime curves infinitely. According to general relativity, the laws of physics break down at this point, and our usual understanding of space and time no longer applies. Penrose's contributions helped us grasp just how extreme these regions of spacetime can be, where time itself becomes a completely different entity than what we experience in everyday life. As much as we've learned from the mathematical and theoretical work on spacetime, we also need to consider its philosophical implications. Jürgen Renn, a historian of science, has explored how the concept of spacetime has shaped our understanding of both physics and the universe itself. Renn suggests that the transition from a Newtonian view of space and time as independent entities to the relativistic view of spacetime as a unified whole fundamentally changed not just how we understand the universe, but how we see ourselves in relation to it. Before relativity, space and time were treated as fixed frameworks that existed outside of us, as though they were containers for the events that happened. After relativity, space and time are no longer separate entities. They're part of a dynamic living structure that interacts with matter and energy. This shift was as much a philosophical revolution as a scientific one, altering the way humans understand not just the cosmos, but the nature of reality itself. Now, as we move into the realm of quantum mechanics, we are faced with another challenge. How do we reconcile this smooth, continuous view of space-time with the strange, unpredictable nature of the quantum world? Quantum mechanics operates at the subatomic scale, where particles behave in ways that defy our classical understanding of space and time. For example, particles can exist in multiple states at once, and their exact position and velocity can never be known with complete certainty at the same time. The very idea of time in the quantum world is murky. In the classical sense, time flows in one direction, with cause preceding effect, but in quantum mechanics, time's flow becomes more difficult to pin down. Events seem to be probabilistic rather than deterministic, and time, in many ways, seems to lose its traditional sense of order. This clash between the smooth space-time of relativity and the uncertain probabilistic nature of quantum mechanics presents one of the biggest challenges in modern physics. We are left wondering whether time, as we understand it, is truly fundamental to the fabric of the universe, or if it's something more malleable and elusive, perhaps even an emergent property of deeper processes yet to be discovered. In the next phase of our exploration, we will venture into the world of quantum mechanics, where the very nature of time and reality itself is under question. How does time behave at the tiniest scales of existence, and how might this differ from the way time operates on cosmic scales? Understanding the quantum nature of time may hold the key to bridging the gap between relativity and quantum mechanics, providing a more unified picture of the universe. But for now, the question remains, how do we truly understand time in the fabric of space-time itself? As we move from the grand scale of space-time to the tiny, seemingly chaotic world of quantum mechanics, the concept of time takes on a very different character. In the world of the very small, the rules were used to break down. Time, which once seemed like a steady and predictable force, is now a slippery and elusive quantity that doesn't behave in ways we can easily predict or control. Quantum mechanics, the theory that governs the behavior of particles at the subatomic level, suggests that time isn't the rigid, unchanging flow we once thought it was. One of the cornerstones of quantum mechanics is the uncertainty principle, introduced by the Danish physicist Niels Bohr and later refined by his colleague Werner Heisenberg. The uncertainty principle tells us that we can never know both the exact position and the exact momentum or speed of a particle at the same time with complete precision. This principle doesn't arise from limitations in our measurement tools, it's a fundamental feature of the universe itself. In other words, the more precisely we try to measure one of these properties, the less certain we become about the other. This uncertainty has profound implications for our understanding of time. In the classical world of Newtonian physics, time flows uniformly and predictably. If you know the position and velocity of an object at one moment, you can calculate exactly where it will be at any other moment. But in quantum mechanics, the idea of a perfectly predictable flow of time simply doesn't apply. Because we can never be sure of a particle's position and velocity at the same time, we cannot predict its future trajectory with absolute certainty. This introduces a probabilistic element to time. Time no longer has a single, clear path, but rather exists as a range of possibilities, each with its own probability. One of the most famous thought experiments in quantum mechanics that illustrates this idea is Erwin Schrödinger's cat paradox, which he introduced in 1935. Imagine a cat locked inside a box with a radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that kills the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, the atom exists in a superposition, meaning it is both decayed and not decayed at the same time until we observe it. By extension, the cat is both alive and dead until we open the box and observe it. This idea, while a bit mind-bending, shows how quantum mechanics challenges our classical understanding of time. The cat's fate isn't determined by any one moment in time, it exists in multiple possibilities simultaneously. Time here isn't a clear, linear progression, but a range of probabilities, all equally valid until the moment of measurement. The paradox raises an important question. If time is so fluid and probabilistic at the quantum level, how does it fit into our more deterministic understanding of the universe? To take this a step further, the idea that time may not be an absolute force of nature, but rather an emergent property, was proposed by the physicist David Bohm. Bohm's theory, called the hollow movement, suggests that the universe is not a collection of separate independent particles, but rather an undivided whole. In this theory, time is not a fundamental aspect of the universe, but emerges as part of a deeper, underlying reality. According to Bohm, time is a result of the way the universe evolves, not a rigid backdrop against which events unfold. This idea challenges the traditional view of time as a fixed external force. Instead, time is fluid and emerges as part of the dynamic, interconnected flow of the universe, a process that cannot be fully understood using classical linear thinking. Bohm's views are echoed in the work of another influential thinker, Roger Penrose, who has contributed much to our understanding of time and its connection to consciousness. Penrose proposed that consciousness itself may be linked to quantum phenomena. He argued that the brain may operate on quantum principles and that the experience of time, or the flow of time, could be influenced by the way quantum processes unfold in the brain. This notion, known as quantum consciousness, suggests that time might not just be a physical concept, but something that is also deeply tied to our perception of reality. According to Penrose, the brain doesn't just perceive time, it might play an active role in shaping how we experience the passage of time. Penrose's theories invite us to think about time in a completely new way. Instead of viewing time as something external and separate from us, we might begin to see time as something that is intertwined with consciousness itself, as a phenomenon that is not only measured by clocks but felt by our minds. If time is emergent at the quantum level, and if our perception of time is somehow tied to the quantum processes in our brains, then perhaps time is more than just a physical property of the universe. It may be something that arises from the interaction between the physical world and the conscious observer. The complexity of time at the quantum level, whether as an uncertain probabilistic force, an emergent property, or a deeply connected part of consciousness, poses many challenges for scientists. The quantum world is far removed from the everyday experience of time that we know. But as we seek to understand how time functions at these incredibly small scales, we are faced with the challenge of reconciling these strange quantum ideas with our larger, more familiar understanding of time as it appears in the macroscopic world, governed by relativity. The question then arises, how does time behave when you bring together the two pillars of modern physics, general relativity, which describes the smooth, predictable passage of time on large scales, and quantum mechanics, which introduces uncertainty and probability? The more we learn about both worlds, the more we realize how little we understand about the true nature of time itself. As we look ahead, we are faced with the possibility that time, as we understand it, may not be a single, unified concept, but rather something that behaves very differently depending on the scale and context. In the next chapter, we will delve into the role of time in the early universe, exploring how it behaves under extreme conditions like those found in the moments following the Big Bang. Understanding how time emerged in the infancy of the universe could offer us new insights into the very nature of time itself, both as a physical and a conceptual entity. The beginning of time is a question that has intrigued humanity for centuries. To understand how time itself came into existence, we must first turn to the Big Bang theory, which offers the most widely accepted explanation of how the universe began. According to this theory, time itself began at the moment of the Big Bang, around 13.8 billion years ago. Before this event, there was no before in the conventional sense. There was no time as we know it, nor was there space. The universe, as we understand it, came into existence at a single point, known as a singularity. This point contained all the mass, energy, and the very fabric of space-time compressed into an infinitely small and dense point. It was here, at this singularity, that both time and space began. At the moment of the Big Bang, the universe expanded rapidly from this point of singularity, creating not just matter and energy, but the very concept of time. The Big Bang wasn't an explosion in the traditional sense. Rather, it was an expansion of space itself. This event marked the birth of both the universe and time, with every subsequent moment marking the continued unfolding of the cosmos. As the universe expanded and cooled, the fabric of space and time itself began to stretch and evolve. But there's another aspect of this early expansion that further complicates our understanding of time. Alan Guth, an American theoretical physicist, proposed a theory known as cosmic inflation in 1979. This idea revolutionized the way we think about the early universe. Guth suggested that in the first fractions of a second after the Big Bang, the universe underwent an incredibly rapid expansion. During this brief period, the universe expanded exponentially, growing by a factor of more than a trillion times in less than a billionth of a second. This period of rapid inflation stretched both space and time, essentially setting the stage for the universe to continue expanding at a much slower rate. The implications of this rapid inflation were profound. Before inflation, the universe was incredibly small, dense, and hot. But this sudden exponential expansion caused the universe to cool down and spread out, allowing matter to form and structures to emerge. Importantly, this rapid expansion stretched time itself. The concept of time as we know it became linked with the expansion of space, and the early moments of the universe became intrinsically connected with this stretching of both space and time. Yet the origin of time itself remains an elusive mystery. While the Big Bang Theory and inflation provide a framework for understanding the early universe, Alexander Vilenkin, a theoretical physicist at Tufts University, introduced an intriguing idea about how time itself might have come into being. Vilenkin's work on the quantum nature of the early universe suggested that time could have emerged from quantum fluctuations. In essence, time may have arisen from the fundamental properties of quantum fields, which existed even before the Big Bang. According to Vilenkin, the universe itself could have been the result of a quantum fluctuation, a spontaneous change in the energy of a vacuum. This idea suggests that time, far from being a constant backdrop, could have emerged from the quantum processes that drove the creation of the universe. The emergence of time from quantum fluctuations leads us into another fascinating theory, cosmological natural selection, proposed by the physicist Lee Smolin. Smolin's theory posits that time is not just a byproduct of the Big Bang, but a fundamental force that drives the creation of new universes. According to Smolin, the laws of physics in our universe are not fixed, but rather they evolve through a process of natural selection. In his view, each universe that forms within a multiverse could have slightly different laws of physics, and those universes with laws that are better suited to the formation of stars, galaxies, and life are more likely to give rise to new universes. This process of cosmological natural selection could, in turn, drive the evolution of time itself, suggesting that time might not be a one-time event, but an ongoing process that shapes the formation of new realities. Smolin's theory connects the evolution of time to the very creation of new universes, suggesting that time is not just a passive feature of the universe, but an active participant in its continual unfolding. Time, in this framework, isn't just a measure of change, it is a driver of change, pushing the cosmos to evolve and giving rise to new possibilities in the ever-expanding multiverse. As we think about time and its role in the creation of the universe, it's impossible not to consider how time might eventually end. While the Big Bang Theory explains the beginning of time, the future of time is just as speculative and mysterious. Some scientists propose that time might eventually come to an end, either through the eventual collapse of the universe, a process called the Big Crunch, or through a more gradual cooling and dying process known as the Big Freeze. In these scenarios, the universe would continue to expand until stars burn out, galaxies drift apart, and the universe grows colder and darker. In such a scenario, time could slow to a stop, as the very forces that drive the passage of time, such as gravity and energy, dissipate. Alternatively, other theories suggest that time might not end at all. Some cosmologists speculate that the universe could undergo a big rip, where the expansion of the universe accelerates to such a degree that space itself is torn apart, including the very fabric of time. In such a scenario, time might be fragmented and no longer behave in the way we understand it today. These ideas about the end of time are speculative, of course, but they highlight the profound uncertainty about time's future and its ultimate fate. And what about time in black holes? The extreme conditions near black holes, where gravity is so strong that not even light can escape, pose yet another challenge for our understanding of time. Inside a black hole, time behaves in ways that seem to defy all common sense. The closer you get to the event horizon, the boundary beyond which nothing can escape, the slower time seems to pass for an outside observer. Inside the event horizon, time itself could be so warped that it loses all meaning, and the singularity at the center of the black hole could represent a point where time breaks down completely. As we venture deeper into understanding time's emergence and its possible end, we realize that time itself remains one of the greatest mysteries of the universe. Whether it's emerging from the Big Bang, stretching out through cosmic inflation, or potentially ending in the far future, time continues to shape our understanding of the cosmos in unexpected ways. As we continue exploring, the true nature of time might still surprise us in ways we can only begin to imagine. The concept of black holes has captivated both scientists and the public for decades, and for good reason. These strange objects, formed from the collapse of massive stars, are the densest regions of space, where gravity is so intense that nothing, not even light, can escape their grasp. But black holes are more than just fascinating objects in the cosmos. They also provide us with one of the most extreme laboratories for studying the nature of time. Stephen Hawking, one of the most influential theoretical physicists of the 20th century, devoted much of his work to understanding the properties of black holes and their connection to time. Hawking's contributions to black hole physics, particularly his work on the event horizon, revolutionized our understanding of the universe. The event horizon is the boundary around a black hole beyond which nothing can escape, not even light. Time behaves in strange ways near this boundary. From the perspective of an outside observer, as an object approaches the event horizon, it appears to slow down. To someone observing this from a distance, the object would seem to freeze in time at the event horizon, never actually crossing it. In reality, from the perspective of the object itself, time continues to pass as it normally would. The closer it gets to the event horizon, the more extreme the effects of time dilation become. This phenomenon, where time slows down as you approach a black hole, is an example of gravitational time dilation, one of the predictions of Einstein's theory of general relativity. The stronger the gravitational field, the slower time moves. This effect has been confirmed in less extreme situations, such as with satellites orbiting the Earth, where time runs slightly faster for clocks in orbit than for those on the surface due to the weaker gravity at higher altitudes. But near a black hole, the difference is extreme, so extreme that time, from an outside observer's perspective, seems to stretch to infinity. As an object crosses the event horizon, however, it's impossible to say what happens to time from a practical standpoint. Since no information can escape a black hole, we can never directly observe what happens beyond the event horizon. Kip Thorne, a theoretical physicist known for his work on general relativity and black holes, expanded on this idea by introducing the concept of wormholes, hypothetical tunnels in space-time that connect distant parts of the universe. Wormholes, if they exist, could potentially allow for faster-than-light travel between distant regions of space. Time dilation effects near these wormholes would be extreme. The strong gravitational fields of black holes, Thorne proposed, could stretch time and space in such a way that they might offer a route through the fabric of space-time, bending time itself. But while wormholes are a fascinating theoretical concept, they come with their own set of problems. First, there's the issue of stability. Wormholes, if they exist, might collapse too quickly for anything to travel through them. Then, there's the problem of time itself. If you were able to travel through a wormhole, what would happen to time at both ends? Would you arrive at the future, or would you be caught in a loop? These questions remain unanswered, but Thorne's work on wormholes continues to shape our thinking about the possibilities of time travel and the strange nature of time near black holes. In addition to time dilation and wormholes, the behavior of time near black holes also touches on another fascinating problem in modern physics, the black hole information paradox. This paradox arises from a disagreement between quantum mechanics and general relativity regarding what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but general relativity suggests that once something crosses the event horizon of a black hole, it's lost forever. In the early 1970s, John Preskill, along with Stephen Hawking and Don Page, helped to develop a theory around the black hole information paradox, suggesting that the information might not be lost entirely, but could be encoded on the event horizon itself. This theory has since evolved, but it remains a critical part of the ongoing debate in theoretical physics. The paradox challenges our understanding of time, as the destruction of information seems to imply that time itself behaves differently under the extreme conditions of a black hole. If information truly vanishes beyond the event horizon, it would suggest a breakdown of the rules that govern time and causality in the universe. Hawking later proposed that black holes might eventually emit radiation, a phenomenon now known as Hawking radiation, which could, in theory, allow the information to escape and prevent the loss of time and events that fall into the black hole. However, this theory is still a topic of active research and has not been definitively proven. Another scientist whose work on black holes and time was groundbreaking is Roger Penrose, a British physicist who contributed immensely to our understanding of singularities, points in space where gravitational forces are so intense that they warp space-time to infinity. In his famous Penrose diagram, Penrose showed how the curvature of space-time around a black hole leads to the formation of a singularity where the laws of physics break down, and time, as we understand it, ceases to behave predictably. At the singularity, time appears to stop, as the curvature of space-time becomes infinite. Penrose's work led to a deeper understanding of what happens at the very centre of black holes. Inside a black hole's event horizon, it's not just matter that's crushed under extreme gravity. Time itself is fundamentally altered. The usual flow of time seems to break down, and our ability to apply the rules of physics to that region of space-time ceases to function in the way we know. This makes the study of time near black holes not only a key challenge for physicists, but also a profound mystery about the nature of time itself. As we ponder the extreme conditions of black holes and the way time behaves near them, we can't help but wonder about the ultimate fate of time itself. The concept of time has already been stretched and warped by gravity, bent by black holes, and linked to the very fabric of space-time. But could time, as we understand it, come to an end? Some theories suggest that the universe may eventually reach a point where time ceases to exist in any meaningful way. In a scenario known as the Big Freeze, the universe could continue to expand indefinitely, with stars burning out and galaxies drifting apart, eventually leading to a state where time, as a useful concept, becomes meaningless. On the other hand, the Big Crunch, another potential fate of the universe, proposes that the universe could eventually stop expanding and collapse in on itself, leading to a contraction that might reverse the flow of time and result in an infinite singular state. The end of time could come in the form of a breakdown of the structure of space-time itself, as everything collapses back into a singularity. And then there's the Big Rip, where the acceleration of the universe's expansion tears apart everything, even the fabric of time itself. All of these scenarios involve the idea of time either ending or being fundamentally altered in extreme conditions. And as we look at the incredible behaviours of time near black holes, we begin to realise that the universe may have a far more complex relationship with time than we can fully comprehend. Time may not just flow in a steady, predictable way, but may instead be a malleable, evolving aspect of the universe, something that bends and changes with the fabric of space-time itself. As we explore the mysteries of time further, we're left with more questions than answers. How does time behave at the edge of a black hole? What does it mean for time to end? These are questions we continue to grapple with as we push the boundaries of our understanding of the universe. And in the next chapter, we'll explore another facet of time, the concept of entropy, and how it shapes our understanding of the flow of time, both on a cosmic scale and in the everyday experiences of our lives. As we continue our journey through the nature of time, we come to one of its most intriguing features, its unidirectional flow, often referred to as the arrow of time. This concept suggests that time always moves forward, never backward. But why is time's progression always in one direction, and how does this relate to the world around us? One of the key insights into this question comes from Ludwig Boltzmann, an Austrian physicist, and his development of statistical mechanics. Boltzmann's work provides a deep connection between the microscopic world of particles and the macroscopic world we experience. At its heart, statistical mechanics is about understanding how the collective behaviour of many particles, such as atoms and molecules, gives rise to the observable properties of matter, like temperature and pressure. One of Boltzmann's key discoveries was that the disorder of a system, known as its entropy, is a fundamental feature of how it evolves over time. To understand this, think of a jar of gas molecules. Initially, the molecules might be concentrated in one corner of the jar, but over time, they spread out to fill the entire jar. The gas molecules will naturally move towards a state where their energy and positions are more evenly distributed. This increase in randomness or disorder is what we call entropy. The higher the entropy, the more disordered the system is. Boltzmann's insight was that the arrow of time, the fact that time only moves forward, can be understood in terms of entropy. According to the second law of thermodynamics, entropy always increases in an isolated system. This law is one of the foundational principles of physics, and it helps explain why time flows in only one direction. Imagine a cup of hot coffee cooling down. Over time, the heat energy spreads out, and the coffee reaches the same temperature as its surroundings. The heat no longer concentrates in one place. It disperses, increasing the entropy of the system. The second law tells us that once the heat is spread out, it doesn't spontaneously gather back into the coffee. In other words, time flows in one direction, toward greater entropy and greater disorder. This ever-increasing entropy is why we perceive time as flowing forward. We remember the past, when things were more ordered, and we experience the present, as things move toward disorder. The increase in entropy is like a clock ticking, and its steady increase sets the rhythm of time itself. It's the reason why you can't unmix the cream from your coffee once they've combined, or why a broken cup doesn't spontaneously reassemble itself. The natural tendency toward disorder shapes our experience of time as something that moves forward, never backward. One of the early contributors to this idea was Max Planck, a German physicist who is often regarded as the father of quantum theory. While his primary focus was on understanding the behavior of energy at microscopic scales, Planck also contributed to our understanding of entropy and thermodynamics at the quantum level. In the early 20th century, Planck's work on quantum theory showed that energy doesn't flow smoothly, as classical physics had assumed. Instead, it comes in discrete packets, known as quanta. This quantum behavior introduced a level of uncertainty and randomness that added further complexity to our understanding of entropy. Planck's contributions also helped to connect entropy with the microscopic behavior of particles. His idea of energy being quantized provided a new way of thinking about how systems evolve over time. Instead of energy flowing continuously, as in classical thermodynamics, energy at the quantum level is transferred in discrete steps, and the distribution of these steps leads to an increase in entropy as systems move toward greater disorder. This relationship between quantum mechanics and entropy deepened our understanding of time as something connected to the behavior of the tiniest particles, and not just something that flows uniformly through the macroscopic world. As we look deeper into how time and entropy are connected, we find even more fascinating theories. One such theory is the idea of dissipative structures, proposed by the Belgian physical chemist Ilya Prigogine. Prigogine's work explored how complex systems, such as living organisms or weather patterns, evolve over time in a way that seems to defy the usual tendency toward disorder. Unlike simple systems, which move toward equilibrium by increasing entropy, dissipative structures can maintain a level of order and complexity even as they evolve. This is because these systems are far from equilibrium. They exist in states where energy is constantly being exchanged and dissipated. For Prigogine, time was not just a simple progression from order to disorder. Instead, it was a dynamic process in which systems can maintain complexity and organization through constant energy flow. This view of time challenges the more traditional picture of time as a force that simply drives systems toward greater disorder. Instead, Prigogine suggested that time is not just a measure of entropy's increase, but a force that shapes the evolution of complex systems. His work opened the door to thinking about time as something more active, an essential feature that drives the behavior of the universe, not just a passive backdrop. As fascinating as these theories about time and entropy are, they also raise deeper questions about how we experience time on a more personal level. We know that our daily lives are shaped by the passage of time, yet our perception of time is not as straightforward as the physical laws of entropy would suggest. We often experience time differently depending on the situation. For example, time may seem to fly by when we're enjoying ourselves or when we're deeply engaged in something, but it can drag when we are bored or waiting for something to happen. This brings us to the relationship between time and consciousness, a subject that has intrigued scientists and philosophers for centuries. How do our minds perceive the passage of time, and how is this perception linked to the thermodynamic laws that govern entropy? Research in neuroscience suggests that the brain has a complex way of processing and perceiving time. The brain constantly uses information from our environment to predict and anticipate future events, and this prediction helps us experience time as flowing forward. Interestingly, this concept of time as something that flows in one direction, toward greater disorder, also connects to how we perceive the world around us. Our brains process sensory information and store it in a way that makes sense of the present, relates it to the past, and anticipates the future. This process is inherently tied to the arrow of time. Our memory systems allow us to recall past events, and our expectations help us anticipate future ones. This dynamic, one-way flow of time is a feature of how our minds work, just as it is a feature of how the universe works. As we delve deeper into the connection between time, entropy, and consciousness, it becomes clear that time is not just a physical concept that governs the universe's progression from order to disorder. Time is also woven into the fabric of our mental lives, shaping how we perceive and interact with the world. It's this dual nature, both as a measurable physical phenomenon and as a subjective psychological experience, that makes time such a captivating and complex idea. As we continue to explore the mysteries of time, we can begin to see how its unidirectional flow, governed by entropy, shapes everything in the universe. From the evolution of galaxies to the beating of our hearts, time is a constant force that drives the progression of all things. And as we look to the future, we will explore how time continues to evolve, both in the cosmos and in the mind, leading to deeper questions about its role in the grand scheme of things. The way we perceive time is one of the most fascinating and elusive aspects of our experience. For most of us, time seems to flow smoothly, a constant march forward that we rarely question. But time, when examined closely, is not just a series of ticking seconds, it's deeply subjective, something we feel, live, and experience differently depending on our mental and emotional states. Our perception of time isn't a simple measurement like the ticking of a clock. It's shaped by how we experience the world around us. One of the earliest figures to explore this notion of time as a subjective experience was William James, an American philosopher and psychologist in the late 19th century. James proposed that our perception of time is not just an abstract concept or external force, rather it's deeply connected to our personal, emotional, and psychological states. In his work on the stream of consciousness, James suggested that time is felt differently depending on the flow of our thoughts and attention. When we're engaged in an activity or focused on something that holds our attention, time seems to fly by. But when we're bored or waiting for something, time seems to stretch on endlessly. For James, time was not just something measured in seconds, but a quality of lived experience deeply tied to our mental states. A similar theory was proposed by the French philosopher Henri Bergson, who took a more philosophical approach to the subjective nature of time. In his work Time and Free Will, published in 1908, Bergson argued that our experience of time, which he called la durée, duration, was vastly different from the mechanical clock-based time we typically think about. According to Bergson, time as we experience it is qualitative, not quantitative. It's the lived experience of time, how we feel it passing in our own consciousness, that defines our perception of time, not the rigid measurements of hours and minutes. When we're absorbed in a moment, time seems to melt away, but when we are disconnected or distracted, time seems to drag. For Bergson, the human experience of time is much richer and more complex than the ticking of a clock. It's a deeply personal, flowing experience. This insight into the subjective nature of time has been supported by modern research, including the work of psychologist Daniel Kahneman, who won the Nobel Prize in 2002 for his work in behavioral economics. Kahneman's research has explored how our perception of time is influenced by our experiences. He and his colleague Ariel E. conducted studies showing that our memories of time spent doing activities are often skewed by how much pleasure or discomfort we felt during those moments. For instance, we tend to remember unpleasant experiences as being longer than they actually were, and pleasurable ones as being shorter. This phenomenon is known as the peak-end rule, which suggests that we judge the overall experience of time based on the most intense moments and how it ends, rather than on the actual duration of the event. So, if a fun vacation ends on a sour note, our perception of the whole trip may be negatively affected, even though most of it was enjoyable. This illustrates how our perception of time is not an objective truth, but a deeply personal, emotional experience shaped by our memories and feelings. As we explore the brain's role in shaping our perception of time, another fascinating theory emerges, one proposed by neuroscientist Jeff Hawkins. Hawkins, best known for his work in artificial intelligence and brain research, has developed a theory about how the brain processes time. In his book On Intelligence, published in 2004, Hawkins suggests that the brain is essentially a prediction machine. Our brains constantly predict what will happen next based on past experiences, using these predictions to guide our perceptions and behaviors in the present. Time, in this model, is not something we passively experience. It's actively constructed by our brains as they process and predict the flow of events. The brain doesn't just wait for events to happen, it anticipates them, using past patterns to predict the future. This predictive model of the brain provides an interesting way to think about how we experience time. Instead of time being a constant external flow, it's something we actively shape through our mental processes, relying on past information to guide our perception of what's happening now and what will happen next. This idea challenges the traditional view of time as a linear, externally controlled force. If our brains are constantly predicting the future, then our experience of time is inherently tied to our understanding of cause and effect. Time is no longer just the steady progression from one moment to the next. It's a dynamic process in which we constantly anticipate and react to the flow of events. This theory could help explain why time seems to move faster when we're focused and deeply engaged in an activity, because our brains are in a constant state of prediction and anticipation, making the present moment seem to move more smoothly and rapidly. As technology continues to advance, these ideas about the brain's perception of time take on new relevance, particularly in the field of artificial intelligence. Ray Kurzweil, a futurist and inventor, has proposed that in the future, machines may have their own perception of time, one that could radically change how we think about it. Kurzweil suggests that as artificial intelligence becomes more advanced, machines will not only be able to process vast amounts of information, but could also develop their own sense of time. This raises fascinating questions. If machines can develop a perception of time, how will it differ from human experience? And could this shift in how machines process time lead to a deeper understanding of time itself? Kurzweil's predictions suggest that as we create more advanced AI systems, we may begin to see time through a completely different lens, one that may challenge everything we know about time as a human experience. These ideas about time, both as a personal experience and a potential machine cognition, suggest that time is more than just a physical phenomenon. It's a fluid, subjective force that shapes our understanding of the world, our memories, and even our future predictions. But as we move further into the realms of technology, neuroscience, and artificial intelligence, our understanding of time may continue to evolve in unexpected ways. In the next chapter, we will explore how advancements in technology may lead to entirely new ways of thinking about time, and how we might even begin to change our relationship with it altogether. Time, as we know it, could soon be something entirely different. In the world of digital systems and artificial intelligence, time is far from the simple, linear progression that we typically experience in everyday life. Instead, time in the digital realm is meticulously measured, synchronized, and controlled. From computer networks to GPS systems, time plays a crucial role in ensuring everything operates smoothly and accurately. But while human perception of time is largely subjective, digital systems and AI require a much more precise, objective sense of time to function. One of the most important aspects of digital time is time synchronization, a process that ensures that all the systems in a network are working on the same clock. In computer networks, especially large-scale systems, even a tiny discrepancy in time can cause errors or inefficiencies. Imagine the global network of servers that supports the internet, or the massive amount of data transferred between systems every second. All these systems rely on synchronized time to ensure that data is correctly time-stamped and flows smoothly between machines. A key example of time synchronization in action is the Global Positioning System, or GPS. GPS relies on a constellation of satellites orbiting the Earth, each of which has an onboard atomic clock. These clocks are synchronized with one another to ensure accurate timekeeping. GPS receivers on the ground calculate their position by comparing the time it takes for signals to travel from the satellites. Even the smallest deviation in time measurement could lead to significant errors in location data. This is why GPS systems must continually adjust and synchronize their clocks with extreme precision, often to within nanoseconds. Without accurate time synchronization, the GPS system would be rendered ineffective, illustrating how crucial time is in the digital world. Beyond synchronization, time in the realm of artificial intelligence and machine learning becomes even more complex. AI systems process data in ways that differ significantly from human perception. Time, for AI, is often a sequence of events or inputs that are carefully analyzed and acted upon, but with a level of precision and speed far beyond human capabilities. For example, in real-time systems like speech recognition or image processing, AI must process and respond to inputs almost instantaneously. The system doesn't experience time the way humans do. Instead, it measures it in strict intervals, down to the millisecond or even microsecond. In machine learning, AI systems learn from patterns in data, and these patterns often have temporal dimensions. Time in this sense is not just a backdrop for events, but is intricately woven into the data the system processes. For instance, when AI systems are trained to recognize speech, they're not just analyzing static snapshots of sounds. They're processing continuous streams of data, analyzing how sounds change over time to understand speech patterns. Similarly, AI-driven recommendation systems, like the ones that suggest movies or music, take into account not only past behavior, but also time-based patterns, such as when a user typically watches a particular genre or listens to specific music. But time in AI isn't always linear, and this is where digital time comes into play. In high-frequency trading, for example, every millisecond counts. Traders rely on algorithms to make buy and sell decisions based on real-time market data, and the faster the system can process information, the better. In such cases, being a fraction of a second ahead of the competition can make a massive difference. Digital time in this context is incredibly precise, down to the millisecond and even microsecond, because the market's fluctuations are so rapid that any delay in processing can lead to missed opportunities. This concept of digital time highlights how, in certain domains, the passage of time is not simply about measuring hours or minutes, it's about making decisions and reacting to events in a fraction of a second, often before human perception could even register what's happening. The idea of digital time extends beyond trading and has applications in many fields that rely on fast-paced data processing. For example, in data centers, where massive amounts of information are processed and stored, precise timing is crucial to managing and distributing data across servers. In these environments, time is not just a passive observer. It actively shapes how data is handled, processed, and transmitted between systems. The importance of time in computing can also be traced back to the work of John McCarthy, a key figure in the development of artificial intelligence. McCarthy, who is best known for coining the term artificial intelligence in the 1950s, also made significant contributions to the development of time-sharing systems in computing. In the early days of computers, each machine could only perform one task at a time. McCarthy's work on time-sharing allowed multiple users to share the computing power of a single machine, each experiencing their own slice of time. This innovation allowed computers to process multiple tasks simultaneously, effectively revolutionizing the way computers were used. Time-sharing was a fundamental step in creating the real-time systems that power much of the modern digital world today. As artificial intelligence continues to evolve, so too does our understanding of how time is represented and processed. In the near future, AI might not only process data based on temporal sequences, but it may develop a more human-like understanding of time itself. The work of futurists like Ray Kurzweil points to a future where AI could one day be capable of experiencing time in ways that are similar to human perception. Kurzweil's predictions about the future of AI suggest that machines might eventually develop a sense of subjective time, perhaps even a sense of past, present, and future, though how that might manifest is still speculative. Kurzweil's work on AI also brings to the forefront the idea that, as machines become more advanced, they may change how we think about time altogether. If machines can develop a perception of time that is more flexible, or even conscious, they may introduce new ways of measuring and experiencing time. For example, machines might be able to adjust their internal sense of time to match different tasks or environments, potentially altering their sense of how quickly time passes or how they relate to the flow of time in the world around them. This raises fascinating questions. How might AI alter our understanding of time in the human context? Will our experience of time shift as we continue to integrate AI into our lives? As we look toward the future, advancements in technology and artificial intelligence are poised to push the boundaries of our understanding of time. Machines are already processing time in ways we could never have imagined a few decades ago. But as AI continues to evolve, it may help us unlock deeper insights into how time functions not only in the digital world, but in the physical world as well. The relationship between time and technology is only beginning to be understood, and as our tools become more powerful and sophisticated, they may offer us new ways to perceive, measure, and even manipulate time itself. In the coming years, the connection between AI and time could redefine our understanding of time, both as a human experience and as a physical phenomenon. As we continue to develop new technologies, AI will undoubtedly play a crucial role in advancing our understanding of the nature of time, and in doing so may challenge and transform the way we think about time in the universe. Time travel, a concept that has captured the imagination of countless generations. The very idea of journeying through time, revisiting the past, or leaping into the future is a thrilling prospect that stirs a sense of wonder, curiosity, and possibility. In fiction, time travel has been portrayed in various forms, each with its own unique set of rules and consequences. Some stories envision time travel as a simple and practical tool, while others dive into the complexities and paradoxes that such a phenomenon might entail. One of the earliest and most famous explorations of time travel comes from H.G. Wells, who, in his 1995 novel The Time Machine, introduced the concept of a machine that could transport a person through time. In Wells' story, the time traveller uses the machine to explore distant futures, witnessing the rise and fall of civilizations and encountering strange and alien forms of life. Wells' novel became a seminal work in the science fiction genre, laying the groundwork for countless time travel stories that would follow. But in The Time Machine, time travel is presented as a relatively straightforward affair. The traveller simply gets into the machine, turns the dial, and is whisked away through the continuum of time. Similarly, in the world of television, Doctor Who, a British science fiction series that began airing in 1963, has made time travel a central theme. The Doctor, a mysterious alien known as a Time Lord, travels through time and space in the TARDIS, a time machine that is disguised as a British police box. Unlike Wells' more limited version of time travel, the Doctor's adventures cover not just the future, but the entire expanse of the universe, both past and present. Time travel in Doctor Who is portrayed as a dynamic and often unpredictable force, one that can change the course of history, create alternate timelines, and even threaten the fabric of reality itself. Through its long history, Doctor Who has explored time travel as both a powerful tool and a potential source of chaos, raising important questions about the consequences of altering time. While time travel in fiction offers a wide range of imaginative possibilities, the question remains: is it actually possible according to the laws of physics? To answer this, we must turn to the theories of Albert Einstein, whose work on relativity fundamentally changed how we think about time. Einstein's theory of general relativity, which was first published in 1915, describes the universe as a four-dimensional fabric of space and time, known as space-time. According to general relativity, space-time can be curved by the presence of mass and energy. The more massive an object, the more it bends the fabric of space-time around it. This bending of space-time is what we experience as gravity. In terms of time travel, general relativity suggests that space-time can be warped in such a way that travel through time could be theoretically possible. One of the most intriguing ideas to come from Einstein's equations is the concept of wormholes. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels in space-time that connect two distant points in the universe. In theory, a wormhole could allow for instantaneous travel between these points, effectively bending time and space. If one end of the wormhole were positioned in the past and the other in the future, it could allow for travel between these two time periods. However, creating or using a wormhole for time travel presents a number of theoretical challenges. First, wormholes are incredibly unstable, and it's unclear whether they could exist in the real universe. Second, even if a stable wormhole could be created, it would likely require exotic forms of matter with negative energy to keep it open. Such matter has not yet been observed, and scientists are uncertain if it even exists. Despite these challenges, wormholes remain one of the most exciting theoretical possibilities for time travel, thanks to the work of physicists like Kip Thorne, a Nobel laureate who has studied the potential for wormholes and their connection to time travel. Thorne has also examined the idea of closed time-like curves, which are paths in space-time that loop back on themselves, allowing for travel to the past. These closed time-like curves could theoretically create a form of time travel, where an object could return to its own past. However, even if time travel were possible, it would not come without complications. One of the most famous paradoxes associated with time travel is the grandfather paradox. The grandfather paradox occurs when a time traveller goes back in time and does something that prevents their own existence, such as accidentally causing the death of their grandfather before the traveller's parent is born. If the time traveller never existed, how could they have travelled back in time in the first place? This creates a logical contradiction that challenges our understanding of time and causality. The grandfather paradox highlights one of the most profound problems with time travel to the past. How can we reconcile the idea of changing events in the past without disrupting the entire flow of history? Over the years, physicists have proposed various ways to resolve such paradoxes, with some suggesting that time travel to the past might be impossible, or that any changes made in the past would create a new timeline rather than altering the original one. Others propose that the laws of physics might inherently prevent paradoxes from occurring, effectively shielding history from changes made by time travelers. One of the most intriguing solutions comes from the idea of the many worlds interpretation of quantum mechanics. This theory suggests that every time a decision is made, or an event occurs, the universe splits into multiple realities, each with its own timeline. In this view, when a time traveler goes back and changes something in the past, they may simply create a new timeline without disrupting the original one. While this idea remains speculative, it's one of the most widely discussed potential solutions to the time travel paradox. Despite these theories, the possibility of actual time travel remains deeply uncertain. While Einstein's equations allow for the theoretical existence of wormholes and closed time-like curves, we have yet to find any experimental evidence for the existence of these phenomena. The challenge of creating and stabilizing a wormhole, let alone using it for time travel, remains beyond our current technological capabilities, and the paradoxes that time travel introduces continue to pose difficult philosophical and logical questions. Nevertheless, the uncertainty surrounding time travel only adds to the excitement and intrigue of the subject. Time travel remains one of the most captivating areas of theoretical physics, with implications that reach far beyond science fiction. If time travel is possible, it would not only change how we understand time itself, but could also revolutionize our understanding of causality, history, and the nature of the universe. As scientific research continues to advance, particularly in the fields of quantum mechanics and general relativity, we may one day find answers to these profound questions, bringing us closer to unlocking the mysteries of time, and perhaps even making time travel a reality. While time travel might remain a speculative idea for now, it challenges us to think about the nature of time in ways that go beyond everyday experience. It pushes the boundaries of our understanding and invites us to dream of possibilities where time is not just something that happens to us, but something that we can actively engage with. Whether or not we ever develop the technology to travel through time, the exploration of this concept will continue to shape the way we think about the universe and our place within it. As we look toward the future of time research, we enter a realm where the boundaries of our understanding are being pushed by the most cutting-edge theories in physics. The search for a unified theory of everything, a theory that would bring together all the forces of nature, including gravity and the quantum forces, is at the forefront of scientific inquiry. At the heart of this search lies the challenge of reconciling two fundamental pillars of modern physics: general relativity, which describes the force of gravity and the structure of space-time on large scales, and quantum mechanics, which governs the behavior of the tiniest particles in the universe. Time, as we know it, plays a central role in both of these theories, but the way it functions within each remains distinctly different. One of the most exciting areas of research in this quest for a unified theory is quantum gravity, a field that seeks to combine general relativity and quantum mechanics into a single framework. Quantum gravity attempts to explain how gravity works at the smallest scales, where the effects of both gravity and quantum mechanics are important. Two of the most prominent approaches to quantum gravity are loop quantum gravity and string theory. Loop quantum gravity is a theory that attempts to quantize space-time itself, proposing that space is not continuous, but made up of tiny, discrete loops of energy. In this view, space-time is granular, much like how matter is made up of atoms. According to loop quantum gravity, time and space are not smooth, infinite continuums, but instead have a smallest possible scale, a quantum of time or quantum of space. This discrete structure could potentially resolve some of the contradictions between general relativity and quantum mechanics, particularly in extreme environments like black holes or the early universe. Loop quantum gravity suggests that time itself might emerge from the interactions of these tiny loops, offering a new perspective on the flow of time. In contrast, string theory takes a different approach. Rather than focusing on the fabric of space-time itself, string theory suggests that the fundamental particles of the universe are not point-like objects, but tiny, vibrating strings. These strings can vibrate at different frequencies, and the different vibrational modes correspond to the various particles we observe in nature. In string theory, the concept of time is deeply connected to the extra dimensions predicted by the theory. Time, in this view, is not just a simple linear progression, but a feature of a much higher dimensional reality. String theory posits that there are multiple dimensions beyond the familiar 3 of space and 1 of time, possibly as many as 10 or 11 dimensions in total. The behaviour of time in this framework is still not fully understood, but string theory offers a potential path to reconciling the forces of quantum mechanics with general relativity. As these theories continue to evolve, one physicist who has made significant contributions to our understanding of time in the context of quantum gravity is Sean Carroll. Carroll, an American theoretical physicist, has argued that time may be a fundamental feature of the universe rather than an emergent property. In his view, time is not just a result of the physical processes that happen around us, but an essential aspect of how the universe operates at the quantum level. Carroll's ideas challenge the traditional view that time is just a measure of change or a backdrop against which events unfold. Instead, he suggests that time itself may be a core component of the laws of physics, helping to explain how the universe behaves on both the smallest and largest scales. According to Carroll, understanding time as a fundamental force could open up new ways to think about everything, from the beginning of the universe to the behaviour of particles at the quantum level. Another key figure in the ongoing research into the nature of time is Carlo Rovelli, an Italian theoretical physicist who has developed a theory known as relational time. Rovelli's relational theory of time challenges the conventional notion of time as a universal absolute flow. Instead, he suggests that time is not a feature of the universe itself, but emerges from the relationships between quantum particles. According to this view, time is not something that exists independently of the physical world, but rather something that is observed and measured by the interactions of particles. Rovelli argues that time is a relative concept, much like space, and that it emerges from the way quantum systems interact with one another. In Rovelli's relational view, the passage of time is tied to the specific processes and events that happen at the quantum level. For example, time as we experience it in our everyday lives is not a fundamental reality, but a result of the interactions between particles, atoms, and larger objects. As these interactions occur, we perceive the passage of time. But at the quantum level, time may not even exist in the way we think of it. Because particles and systems can be in multiple states at once, the passage of time may appear to be fundamentally different. Rovelli's work provides an intriguing framework for thinking about time, one that questions our traditional understanding and opens up new possibilities for how we might experience time in a quantum universe. These theories, loop quantum gravity, string theory, and relational time, represent some of the most innovative and thought-provoking ideas in modern physics. But what might they mean for our understanding of time itself? If time is, as these theories suggest, not a constant, but something that emerges from the relationships between particles, the very fabric of space-time, or the extra dimensions of string theory, then time may not be as fixed or unchangeable as we once thought. The flow of time, traditionally seen as something that moves forward in a uniform, linear fashion, could instead be far more dynamic and flexible, influenced by the conditions of the universe, the interactions of matter, and the quantum laws that govern the behaviour of particles. The implications of these theories are profound. If time is truly emergent, or if it can be manipulated by the fundamental forces of the universe, then it may be possible to unlock new ways of understanding and even controlling the passage of time. Concepts like time travel, previously relegated to the realm of science fiction, could become more grounded in scientific possibility, and with advancements in quantum computing and further exploration of the quantum nature of space-time, the next breakthroughs in our understanding of time could be just around the corner. As we continue to investigate the nature of time through quantum gravity and related theories, we are likely to uncover new insights that could change how we perceive the universe, the very fabric of reality. Space, time, and everything in between may be far more interconnected and flexible than we can currently comprehend. The future of time research holds the promise of deeper answers to some of the universe's most profound mysteries, from the beginning of time itself to the future of cosmic evolution. These advancements could not only transform our scientific understanding, but also revolutionize how we experience and relate to time in our everyday lives. Imagine a reality where every choice you make, every action you take, creates a new version of the universe. In this view, there is no single, unchangeable timeline. There are countless timelines, each branching off in different directions based on the infinite possibilities of the universe. This is the essence of the multiverse theory, a concept that suggests our universe may be just one of many, each existing independently but potentially interacting in ways that challenge our conventional understanding of time. The idea of the multiverse is a fascinating and increasingly plausible theory in modern physics. Max Tegmark, a physicist known for his work in cosmology, has been a leading proponent of the mathematical interpretation of the multiverse. According to Tegmark, the multiverse is not just a fanciful idea, it's a direct consequence of the mathematical structures that underpin reality. He suggests that just as different solutions to a mathematical equation can lead to different outcomes, the universe itself may have multiple solutions, each giving rise to a different universe. This view of the multiverse, known as the mathematical multiverse, posits that all possible mathematical structures actually exist in their own right as parallel universes. This means that in this framework, time itself could behave differently across the different universes, depending on the rules that govern each one. Building on the concept of parallel universes is the many worlds interpretation of quantum mechanics, a theory that proposes every possible outcome of a quantum event actually occurs, but in separate branching realities. In the famous Schrödinger's cat thought experiment, for instance, a cat is both alive and dead in a quantum superposition, and the many worlds interpretation suggests that each possibility exists in its own parallel universe. This leads to the creation of multiple timelines, each one representing a different possible outcome of events. In the many worlds interpretation, time isn't just a single, continuous flow. It's divided across an endless number of branching timelines. Each universe is like a parallel timeline, with its own version of the present, past, and future. As decisions are made or events unfold, they create new branches in the timeline, leading to multiple versions of reality existing simultaneously. This concept of time challenges the traditional view of time as a single, unidirectional flow that everyone experiences in the same way. In the multiverse, time may move in different directions, at different speeds, and with different rules in each of the parallel universes. This idea of multiple branching timelines is deeply connected to the work of David Deutsch, a physicist known for his contributions to the many worlds interpretation of quantum mechanics. Deutsch proposes that the multiverse is not just a theoretical possibility, but a necessary consequence of the quantum mechanics that govern the behavior of particles. According to Deutsch, every time a quantum event occurs, the universe splits into different versions, each corresponding to a different outcome. In this view, time behaves differently in each of these parallel universes, with each universe experiencing its own unique flow of time. Deutsch goes even further in suggesting that time's flow may differ drastically between parallel universes. In some universes, time could move at a faster rate, while in others it could appear to be almost frozen. The existence of these multiple, diverging timelines opens up a host of possibilities for how time could function in ways that defy our traditional understanding. The implications of this are profound. If time is not fixed, but instead exists in a myriad of forms across the multiverse, then the nature of reality itself may be far more flexible and diverse than we ever imagined. The idea that time might behave differently across parallel universes challenges some of our most deeply held beliefs about the nature of reality. In our everyday experience, time seems to be an unchanging constant. It moves forward, and we age as it does. Events unfold in a linear fashion, and we make decisions based on the assumption that the future is shaped by the past. But in the multiverse, time is no longer a simple, universal flow. It is a much more complex and fragmented phenomenon. Every choice, every quantum event could create a new version of time, leading to a universe where time behaves in radically different ways. This concept not only raises questions about the flow of time, but also about the very nature of causality. In our universe, cause and effect are intimately tied to the passage of time. Events happen in a specific order, and we can trace a direct line from the past to the present, and from the present to the future. But in a multiverse with multiple, diverging timelines, causality becomes less clear. Events in one universe may not affect the course of events in another universe, and the traditional idea of cause and effect may not hold in the same way across parallel realities. The implications of these theories extend beyond just the nature of time. If the multiverse exists, it suggests that our reality may not be the only one, and that there are countless other universes out there, each with its own unique laws of physics, its own versions of time, and its own histories. This could lead to a new understanding of the cosmos, one where the universe we experience is just one of many, each unfolding in its own way, with its own flow of time. As we continue to explore the multiverse and the many worlds interpretation, we are faced with some profound questions. What does it mean for time to behave differently in parallel universes? How does the flow of time connect to the broader structure of the multiverse? And what does this say about the nature of reality itself? These are questions that challenge our current understanding of physics, and they may offer new insights into the fundamental nature of time, space, and existence. In the coming years, advances in quantum mechanics, cosmology, and the study of the multiverse may lead to new breakthroughs in our understanding of time. Theories like those proposed by Tegmark, Deutsch, and others are helping to reshape how we think about the universe and our place within it. As we push the boundaries of what we know, we may discover that time and the very fabric of reality are far more complex and mysterious than we ever imagined. The multiverse may hold the key to unlocking some of these mysteries, offering new perspectives on time's flow, its relationship to the cosmos, and its role in shaping the realities we experience. Time is something we all experience, yet our perception of it is deeply personal and subjective. It's a fascinating interplay, as time affects us physically and mentally in ways that we often take for granted. While the ticking of a clock is universally constant, the way we experience time, how it flows, stretches, or contracts, can be shaped by our mind, our attention, and even our emotions. This connection between time and consciousness has long been a subject of exploration in both philosophy and neuroscience, as scientists and philosophers have attempted to understand how our brain perceives time in the present, past, and future. Our perception of time is central to how we experience the world around us. The brain is constantly processing information, drawing on memories of the past, predicting the future, and adjusting its awareness to the present moment. But time, as we experience it, isn't a steady flow. Instead, it often feels elastic, speeding up when we're immersed in something enjoyable, or dragging when we're bored or waiting. This subjective experience of time isn't just a psychological quirk, it's a crucial part of how we navigate and interpret the world. Understanding how the brain processes time can help us better grasp both our internal experiences and the nature of time itself. One of the most intriguing theories of time and consciousness comes from Roger Penrose, a renowned British physicist and mathematician who proposed that quantum mechanics plays a critical role in human cognition and perception. Penrose's theory, known as quantum consciousness, suggests that our conscious experiences are deeply tied to quantum phenomena in the brain. He theorizes that certain quantum effects, particularly those related to the behavior of particles like electrons, are involved in the emergence of conscious thought. In this view, the brain's interaction with quantum processes could explain some of the more mysterious aspects of consciousness, including our perception of time. Penrose suggests that time in this framework may not be experienced in the same way it is in the physical world. While time in the physical world is a continuous flow, quantum processes within the brain might allow for a more flexible perception of time, one that can stretch or compress depending on the state of the brain. For example, moments of deep concentration might cause time to seem to fly by, while periods of anxiety or boredom might cause time to drag. Penrose's theory introduces the possibility that our perception of time is not just shaped by the external world, but also by the internal quantum processes occurring in our brains. Building on this, Francis Crick and Christoph Koch, two leading neuroscientists, explored the nature of consciousness and its relationship to the flow of time. Crick, who is best known for his discovery of the structure of DNA, later turned his attention to the mystery of consciousness. He argued that consciousness arises from the activity of neurons in the brain, particularly from the synchronized firing of neurons in specific patterns. According to Crick and Koch, the experience of time is deeply tied to these neural patterns, as the brain constantly processes sensory input and integrates it with our memories and expectations. In their work, Crick and Koch suggested that the flow of time is not something that exists externally, but is instead a product of how the brain processes information. The way we perceive time is based on our ability to make predictions about the future, recall memories from the past, and integrate these with the current moment. The synchronization of neural activity in different parts of the brain helps to create a cohesive sense of time, allowing us to experience events as flowing from one to the next. In this sense, time isn't just something we observe, it's something that the brain actively constructs based on its internal processes. But as we think about time's relationship to consciousness, we also need to consider the idea of subjective time, the way time feels in our minds, as opposed to its objective, measurable passage. Subjective time is deeply influenced by our emotional and mental states. When we're enjoying ourselves, time seems to pass quickly, almost as if it's slipping away unnoticed. Conversely, when we're in discomfort or anxiety, time seems to stretch endlessly. This phenomenon is a reflection of how our consciousness shapes our perception of time, and it's a key part of how we experience the world. The idea that time feels elastic is particularly evident when we look at how we experience the past, present, and future. The past is something we reflect on, the present is what we experience in the moment, and the future is what we anticipate. However, these temporal experiences are not as distinct as they may seem. The present moment, for instance, is always in flux. We only ever experience the present as a fleeting moment between the past and the future, and yet we often feel as though time is stretching or contracting depending on what's happening in the moment. Our brain doesn't just observe time, it actively constructs our sense of the present, pulling from memories of the past and predictions of the future. In the realm of artificial intelligence, AI, this relationship between time and perception becomes even more intriguing. AI systems process time in ways that differ from human cognition. Unlike the human brain, which operates based on subjective experiences of time, AI models often rely on precise, objective measures of time to make decisions. In many AI applications, time is quantified in strict intervals, milliseconds, microseconds, or even nanoseconds. In systems such as real-time decision-making or machine learning, AI must process information and make decisions in a matter of seconds, constantly adjusting its understanding of time as data is processed. For example, AI systems used in high-frequency trading are designed to react to market data in real time, often processing vast amounts of information and making decisions within milliseconds. In these systems, time is treated as an input that must be measured and processed with extreme precision. Time in AI doesn't bend or stretch as it does in human perception. Instead, it is something rigid and quantifiable, and AI models must operate within these precise constraints to function effectively. As AI continues to evolve, the intersection between time, consciousness, and machine cognition may become more pronounced. While human perception of time is influenced by emotions, experiences, and the quantum processes in the brain, AI operates based on strict mathematical models and data-driven algorithms. But as AI systems become more advanced and more capable of mimicking human-like cognition, it's possible that future technologies could create machines that develop a more human-like experience of time. If AI systems could one day learn to integrate subjective experiences of time, much as humans do, our understanding of time itself could be transformed. This potential for machines to alter our understanding of time is especially significant when we think about the implications for consciousness. If AI systems are able to simulate or even develop their own perception of time, it could change the way we think about consciousness itself. Could machines eventually perceive time in ways that are fundamentally different from us? Could they experience time as a fluid, subjective force, or would they always see it as a rigid, external system? These are questions that will continue to shape the future of both AI research and our understanding of time. As we look toward the future, advancements in quantum consciousness and artificial intelligence will likely continue to influence how we think about time. The more we learn about how the brain processes time, how AI systems interact with it, and how consciousness itself might evolve, the more we will reshape our understanding of this most elusive and fundamental force. Time, it seems, is not just a simple ticking of the clock, but a dynamic, ever-evolving concept that is deeply intertwined with our experience of reality itself. As we reflect on the journey through time that we've taken, we can appreciate just how much our understanding of this mysterious force has evolved. From ancient civilizations marking the hours with sundials to the abstract theories proposed by Einstein and Penrose, time has long been a subject of fascination and mystery. Ancient philosophers like Zeno of Elea and Augustine of Hippo first pondered its nature, questioning whether time was something that flowed independently of us or something we experienced subjectively. These early reflections laid the groundwork for much of the deeper scientific inquiries that followed. In more recent centuries, time has been explored through the lens of cutting-edge physics. Einstein's theory of relativity revolutionized our understanding of time, showing that it's not a universal constant, but a dynamic, flexible part of the universe. time can bend, warp, and stretch, influenced by speed, gravity, and the curvature of space-time itself. The mysteries of time deepened further with quantum mechanics, where particles behave unpredictably, and the flow of time is uncertain at the smallest scales. Theories like loop quantum gravity and string theory aim to unify these two domains, proposing that time may be an emergent property of the universe, influenced by the interactions of particles and quantum fields. Yet, even as we uncover more about the nature of time, much remains unknown. Time travel, a concept that has fascinated us for centuries, is still a subject of theoretical exploration. Theories of the multiverse and many worlds' interpretation of quantum mechanics offer tantalizing possibilities that time could behave in radically different ways across parallel universes. And still, the subjective experience of time, how we feel time passing in our minds, from the fleeting moments of joy to the long stretches of waiting, remains deeply tied to our consciousness, our emotions, and our memories. Looking toward the future, the potential discoveries in time research are vast. As our understanding of quantum gravity advances, we may uncover entirely new perspectives on how time operates, not only on the scale of galaxies and black holes, but also at the tiniest subatomic levels. The rapid growth of artificial intelligence offers another exciting frontier, where time, memory, and cognition may intertwine in ways we've never imagined, reshaping our very perception of time itself. As AI continues to evolve, machines may one day develop a different experience of time, and this could offer insights into human consciousness, pushing the boundaries of how we understand our place in the universe. But even with all these advancements, time remains as elusive and profound as ever. It governs the ebb and flow of everything around us, our hearts, the changing of seasons, the rise and fall of civilizations. It shapes the fabric of reality itself, driving the forces that define the universe. Yet, despite our growing understanding, time still holds countless mysteries. How does it emerge from the quantum world, and what role does it play in the very structure of the cosmos? Can we truly manipulate or even travel through it, as we see in science fiction? These are questions that may take centuries more to answer. As we continue to explore time, both in the realms of physics and consciousness, we're reminded of just how central it is to our understanding of everything. Time isn't just a measure of change, it is the thread that connects all of existence. From the smallest particles to the vast reaches of the cosmos, time is woven into the fabric of reality itself. As we continue to ask the deep questions about what time really is, we move ever closer to unlocking the mysteries that govern the universe. Yet, as we look ahead, we can't help but feel that there is still so much more to discover. Endless possibilities that time itself may still be hiding from us. The journey to understand time is far from over, and its ultimate secrets may hold the key to understanding the nature of existence itself.